This video is going to introduce our work on deep symbolic superoptimization without human knowledge. Symbolic superoptimization refers to the task which, given a symbolic expression, finds a simplified equivalent substitute, which is very important to reduce unnecessary computations during program compilations. Recently, there has been increasing research attention on applying deep learning methods for symbolic superoptimization. These existing methods can be roughly divided into two categories. The first category is to learn a mapping from long expressions to short equivalent expressions in a supervised manner. Such method requires a human-constructed dataset of equivalence pairs. The second category has access to a set of human predefined simplification rules and learns to apply the appropriate rules to simplify a given expression via reinforcement learning. As you can see, there is a common limitation in both types of existing works. They both require some human predefined equivalent pairs or rules. However, over-relying on human expertise can lead to a learning bias, because it is impossible for humans to exhaust all necessary equivalent rules. Motivated by this, we propose Human-Independent Symbolic Superoptimization, or HIS, which is a reinforcement learning framework for symbolic superoptimization that does not rely on human knowledge. Before I discuss the framework of HIS, it is important to point out that HIS processes the expressions not as strings, but as expression trees. The advantage of the tree representation is that even a randomly generated expression is syntactically correct, which greatly reduces the exploration difficulty of reinforcement learning. With this in mind, let's look at the framework of HIS. HIS consists of three modules. The first module is called the tree encoder, which encodes the input expression and produces an embedding for each node using a tree LSTM. The encoding process is bottom-up, so the embedding of each node summarizes the information of the entire subexpression led by the node. The second module is called the Subtree Selector, which is a feed-forward network that takes all the embeddings and produces a score for each subtree. The subtree with the highest score is selected for simplification, and the corresponding embedding is passed to the third module. The third module is called the tree decoder, which takes the embedding and generates a simplified equivalent expression top-down using a tree LSTM, with an attention mechanism on the input symbols. Once the simplified equivalence is found, it will replace the original subtree. The resulting expression is fed into HIS again for a next round of simplification. The iteration terminates when some termination criteria are hit. The entire model is trained end-to-end with a reinforced framework, where the reward is determined by whether the output expression is equivalent and its length. To facilitate exploration, we adopt a learning curriculum where the input expressions gradually become longer. We evaluate our model by comparing it with some human-independent searching methods as well as some human-dependent state-of-the-art algorithms. Both results show that our model is able to find more and shorter equivalent expressions. Here is a comparison between the simplification rules discovered by HIS and the human predefined rules in Halide. As can be seen, HIS finds a lot more rules, many of which cannot be deducted from the human predefined rules. Let's look at the simplification process on an example expression. An important rule to simplify this expression is that an expression divided by a constant and then multiplied by the same constant should be equal to the expression itself. As can be seen, HIS learns this rule, and thus can reduce the expression to its simplest form. However, this rule is missing in the Halide predefined rule set, and thus the Halide algorithm, which only uses this predefined rule set, gets stuck. This comparison illustrates why solely relying on human predefined rules is insufficient. To learn more about the model, you're welcome to read our paper and code. Thank you for your attention.